Okay, so today is capacitor day. So this is an HS2. No, it's a what do you call these things? PHET, PHET simulation. So it's talking about capacitors, and so remember the capacitors are conducting plates, and they're used for storing energy in electric circuits. They've got new capacitors that are made that can store a huge amount of energy, electrical energy, and they're using that for energy storage in general. Supposedly they use activated carbon, which is the stuff that they make at the mill in the carbon department, or Ingevity now. So the reason we're using activated carbon, it just increases the surface area of where the charge can be stored. But the classical capacitor is two parallel plates of conductive material, and they're attached by wires to some source of electrical potential, like a battery. So here's my battery. And what happens is you've got your battery which is unhooked, so there's zero voltage, and at that point there's nothing happening. If I can get it to go to zero. I don't quite want to go to zero, but there's nothing that's going to push electrons to one plate and pull electrons from the other plate. But if you apply voltage to this circuit, you create an electric field inside the wire, and so the electric field pushes electrons into this plate and pulls out of electrons out of this plate. Now, they don't actually go all the way around. It's not like the electrons go up here and over there, through the battery, down there. What happens is the electrons, the movable electrons that are on this plate just get pulled into the wire here, and then everything gets shifted around a little bit, and then the excess electrons that are here, or the electrons that are here, get pushed into the plate. So they don't go all the way around. And this is what there were two things that were shown in the video that you're supposed to watch, that the capacitance is the ratio of the amount of charge that you can put on the plates divided by the voltage applied, and you can rearrange this in three different forms. So this is defining what capacitance is. If you have the capacitance and you apply voltage, that tells you how much charge is on each plate. Or if you have charge on a plate and you know the capacitance, then you can figure out what the voltage is. So it's just the same equation, just solved for three different things. And the other one was the capacitance is equal to this constant mu0, which is related to Coulomb's constant, times the area of the plate divided by the distance between the plates. Another thing was the electric field between the plates of a parallel plate capacitor is equal to the voltage applied divided by the distance between the plates. So those are the equations we're playing with. So I'm just going to demonstrate it here. And the amount of charge is indicated by the number of plus and minuses. So you can vary the spacing here. So you can see as I increase the spacing, I'm decreasing the capacitance, which means that for a given voltage applied, I get less charge. So as I move the plates apart, the charge on the plates goes down. So to maximize the amount of charge on the plates, I want to move the plates together as closely as possible. The other thing that affects the capacitance is the area. So if I take this plate and just make it bigger, what happens is that the amount of charge per unit area stays the same, but because the area is bigger, the total amount of charge gets bigger. So increase the area, that increases the capacitance, which then, for a given voltage applied, increases the amount of charge. So to make my capacitance as big as possible, I try to get them as close together as possible and increase the area as much as possible. Now, between the plates is an electric field, and you can click here, electric field lines. So there's the electric field lines, and you can see that the electric field is the voltage divided by the distance. So as I increase the separation distance, the number of lines per area go down. So as I close this together, the electric field gets bigger. And that's because these charged particles are closer to each other, and they're going to attract, since they're opposite charge, they're going to attract each other, and you're going to have just a more, electric field depends upon the distance from the charged particle to a point in space. And that's where the energy is stored, is in this electric field. So if you have this stored energy, you can see as I separate the plates, the amount of energy stored goes down. Or if I increase the area, the energy stored goes up. And if you look at, let's take the electric field lines off. Here's my electric field meter. You can see the same thing. As I increase the separation distance, the electric field gets smaller. And the electric field is going from the positive charge to the negative charge. Remember, electric field goes out of a positive charge and into a negative charge. So it makes sense that the electric field between capacitor plates goes from the positive to the negative charged plates. So that's the basic idea of the things that affect it. Now, this was also mentioned in the lecture video that you should have watched, is you can increase the capacitance of a capacitor by decreasing the separation, increasing the area, or you can put this stuff called a dielectric material in between the plates. So if I put in here energy stored, and I bring this dielectric material in, you'll see that the energy stored goes way up there. Okay, so it allows more electrons to be transferred from one plate to the other. And the way that works is, you can see right now you've got these purple plus signs in here, which represent that it's kind of a neutral situation. But in a dielectric material, they are polar. The molecules are polar in some ways. So without the electric field applied, so out here, when they're not between the plates, there's no electric field applied to them. So they're just randomly oriented around. All the plus and minuses of the charge, the things that are movable, are randomly distributed, and therefore there's no net direction. But when you stick the dielectric material in there, these things all they all line up. And because this is the positive plate, the negative part will align up to that, and the negative charges will align to the positive charges will align to the negative plate. So you see when I stick that in, that the negative part of this molecule point towards the positive plate, and the positive part of the material points towards the negative plate. And what that does is it creates an electric field, because now you've got everything. You got plus charges up here and negative charges down there, and so it creates its own electric field. And this electric field counteracts the electric field that results from the interaction between the two plates. So if I show the electric field lines, let me show you that. So here's the electric field lines. So when I bring this dielectric material in, you'll see, well, it didn't increase the, well, what it actually does is these molecules, like I said, it kind of goes the opposite direction, creates electric fields in the opposite direction that allow more of these charges to be drawn onto the plate. Okay, now, for what we're doing today is we're going to do one of these problems that we went over in class, well, actually, again, in the notes. So hopefully you watched the video. Well, no, you guys were here. We did this in class. So we're going to go through an exercise like the one I did in class, whatever day that was, Monday. But I wanted to just show you how these things interact. So if we put a voltage across a single plate, we get this situation. Now, if I put two plates in series, so they're connected like that, what you would find is that the negative charges here, well, let's explain what happens. Okay, so there's no voltage on the battery. When you apply the voltage to the battery, you create an electric field inside the wire, and it starts to pull negative charges this direction, which leaves the plate positively charged. This positively charged plate then attracts the electrons that are in this wire and pulls them into this plate. So this plate becomes negatively charged. But because I'm pulling the negative charges into here, they have to come from somewhere, which is this other plate from the other capacitor. So when I do this voltage thing, I'm going to take electrons from here, put them into here, and then push the ones that are there into there. So that's what happened. The thing is that the voltage across each capacitor, the sum of the two voltages across the capacitor has to be equal to the total voltage applied to the system. So when you have one capacitor, you have 1.5 volts applied to this capacitor plate. But if you have two in series, you only have, say they're equal, say they have the equal capacitance, then you're going to have half the voltage drop across here and half the voltage drop across here. And if the voltage is half, then the amount of charge is half. So as you add more capacitors in series, you're going to decrease the amount of charge on these plates, because again the total voltage drop here has to be 1.5 volts according to this battery. So if you have a third of 1.5 and a third of 1.5 and a third of 1.5, the amount of charge on each plate has to be a third. So the equivalent single capacitor of these three capacitors is going to be 1/3 if they're all equal to each other. 1/3 the capacitance of each individual capacitor. Now if you have one capacitor that's closer and this has more capacitance, what will happen is that more of the voltage drop will actually be across the these two plates. We could see that if we get our voltmeter here. So if I measure the voltage across these two plates, it's 0.234 volts. If I go down here, the voltage across this plate is 0.66 volts. And if I measure the voltage across these two plates, it's 0.633 volts. So, you think the capacitor with the largest capacitance would have the largest voltage drop, but it's the opposite. It's because the 1 over the equivalent capacitance of capacitors in series is equal to 1 over the sum of the reciprocals. And we'll see that when we do our example here. So, and it's because what has to be common between all three of these is not the voltage. What has to be the same is the amount of charge, because any charge that I get here I have to steal from there. Any charge that I have from there I have to steal. So the charge has to be distributed equally between the three capacitors when they're in series. And if the charge is the same but the capacitance is higher, if we go over to our thing here, if the charge is the same but the capacitance is higher, then the voltage for the higher capacitance capacitor is going to be smaller. So that's why we're seeing this kind of behavior. Okay, let's go to now. When you're in parallel, what happens is that the 1.5 volts is applied to each plate. So you get this again. If they're equal, you're going to get the equal charge on each plate. But if I change the capacitance of one of them, you still have the same voltage applied. So in this case, the higher capacitor one is going to have more charge. It's going to have the same voltage just because of the way this thing is connected. Because this wire is connected to here without anything in between. You have the same voltage applied across each of the capacitors in parallel, whereas when they're in series, you have the same charge. Same voltage, same charge. Same voltage. So here we've got the same voltage, different charge. Here we've got different voltage, same charge.
And then here's what we got: 2 in series, and so this is where you've got 2 in series and 1 in parallel. So what you have here is, if I take my voltage probe, you'll see the voltage across this single capacitor is 1.5 volts. If I go over here, the sum of these two, the voltage drop across both of these has to be 1.5 volts. So I get 0.75 volts across this capacitor, and I get 0.75 volts across that capacitor. Now, if I increase this capacitance, what will happen is this voltage will go down, and this voltage will go up. You can see when I change this capacitance, how if you watch the voltage here, as I increase the capacitance, the voltage across the lower capacitance capacitor increases, and hence this one has to decrease to match it up. But always the sum of these two voltages, the sum of the voltage drop across here and the voltage drop across here have to be the voltage that's applied through the battery. Okay, so let me hand out what we're going to work on for the next half hour or so. It's like I said, it's like what I did in class. So if you were trying to use capacitors to blow something up, or to do some dangerous stuff, then would you store them, would you do it in series or in parallel? The answer would be parallel, because you're going to apply you're going to charge them up using some kind of battery or power supply. And so if you apply the same voltage to each capacitor, then you're going to get the sum of the charges. Pardon me? Blowing something up. I do have a video. It's pretty fun, which I might show. Maybe we'll show that halfway through this assignment, so we have a break, get to see things. Okay, so let me draw this on my screen. I think I erased. Well, no, I can find this. Let's see. So I got okay, so here we are. I haven't worked this, but there shouldn't be any problem. There's nothing to mess up. It's not one of those cases where I can give you a problem that's going to turn out not to work out. So what we have is we have these two capacitors in parallel, these two capacitors in parallel, and these capacitors in parallel. And the rules are that for parallel capacitors, that the equivalent capacitance is equal to just the sum of the capacitors. Okay, so however many capacitors you have. When they're in series, you have 1 over the equivalent capacitance is equal to 1 over the first capacitance plus 1 over the second capacitance plus 1 over the third capacitance, and however many you have. So if you have 2, you have 2 terms. So the first thing it says calculate the equivalent capacitance of the circuit. We can replace all of these 7 capacitors with 1 capacitor. And if I looked at, if I took a current meter and stuck it in the line and looked at the behavior of the circuit, it would behave the same whether I had 1 equivalent capacitance or 7 individual capacitances.
So the first thing we're going to do is we're going to combine the ones that are in parallel into equivalent capacitances. So we're going to replace these two capacitors with a single capacitor. We'll call that capacitor A. We'll call this part A of the circuit. This will be part B, and this will be part C. So we're going to replace the first two capacitors there with an equivalent capacitance. And then we'll do the same thing for this part. And then we'll do the same thing for the third part. And those will all be connected back through the battery. Notice the symbols I'm using here. Two parallel lines the same length are capacitors. If you have two lines that are parallel but not the same length, then that's a battery. And the longer side is the plus side, and the shorter side is the negative side. So this would be a battery like a AA battery or whatever. And I'm saying that's 3 volts. Okay. So all we have to do is just figure out what these are. Well, if we go back here to our equation, for parallel capacitors, we just add them together. We just add the values together. So the equivalent capacitance A is just 1 plus 2, which is 3. And the equivalent capacitance for B is just 3 plus 5, which is 8. And the equivalent capacitance C is 1/2 plus 2 plus 7/2, which is 6. So we're gonna write those in here. This is 3 farads. Now normal capacitors aren't this big, but I just didn't want to have to deal with 10 to the minus 6 all the time. So the procedure's the same. So I've replaced each of the sets of parallel capacitors with a single equivalent capacitance. Now once you've gotten rid of all the parallel parts, then we can analyze these series capacitors as using the parallel capacitance equation to simplify these 3 into a single one. So finding equivalent capacitance is really not that hard. Now let's say if I put another capacitor right here in series, what would I do? Well, I combine the two that are in series into a single capacitor, and then I would add these 3 together. So you kind of go to it's kind of like parentheses, you know. This is in one parenthesis, and this is another parenthesis. This is another one. If you had another capacitor here in series with this one, so it was connected to the end of this and then through there, you would do this operation first, and then you would do this operation. Then you do this one and this one together, and then you put all these 3 together. So that's how you'd handle even more complicated arrangement. Okay, so now the next thing we do is, and I'll let you calculate this. The math's a little harder. That math was easy. So then you would replace the 3 equivalent series capacitors into a single capacitor. And so we'll call that equivalent capacitance. We'll just call it the total equivalent capacitance. And so we have that the equivalent capacitance is equal to 1 over equivalent capacitance A plus 1 over equivalent capacitance B plus 1 over equivalent capacitance C. So that's 1 over C equivalent is 1/3 plus 1/8 plus 1/6. So what I'm asking you guys to do is to calculate the answer. So what you'll do is you'll find out, I don't want you to do it in fractions, don't use your calculator. Well, you might use your calculator to add and subtract, but find the common denominator for these 3 terms. Combine the 3 fractions so you'll have a single fraction, and then just take the reciprocal. And the thing about series capacitors is that the answer is always less than the smallest capacitor. So the smallest capacitor is 3 farads. So your answer should be less than 3 farads. series capacitors always lower the capacitance, lower the amount of charge that you can obtain. You're like, why would I do that? Why would I put capacitors in? Well, there isn't too many cases that you would do that, but that's, I guess, if you had you needed an exact capacitance, and if you wanted to match it, not necessarily have the most capacitance, but to have a particular value of capacitance, you could do that. Yeah, it's fraction day. We did that. Calculus, we did fractions a lot. Now we're doing it in physics. So that's when people who take pre-calculus say, I hate fractions. So like, too bad. See if you can do it in your head, right? That's what I'm going to do, just to challenge myself. Let's see. Okay, see if I got it right or not. Oh, is it the other way around? Okay. Are you sure? So I was right, huh? Yeah, so what I did was I said, this is going to be 8, 3, and 4. 8 plus 3 is 11, plus 4 is 15. 15 24ths, so that's 24 15ths. And they have a common factor of 3, so it's 8 fifths. Okay, just in case you didn't get what I just said. That's why. Yeah, this fraction turned out to not to be too bad. You're lucky that I chose what I did. Okay, so you get 1 over the equivalent capacitance is 8 24ths plus 3 24ths plus 4 24ths. Because you have to multiply this by 8, this by 3, this by 4 to get 24ths. So when you add those together, you get 15 24ths. So the equivalent capacitance is 24 15ths, which is 8 fifths. Okay, so that is the equivalent capacitance, 8 fifths farads. And as I said, it's small. It's always smaller than the smallest capacitance that you start with. And the closer they're together, if these are all 3s, then you'd end up with, what would you end up with? 1/3 plus 1/3 plus 1/3, which is 1. Reciprocal of 1 is 1, which is less than 8 fifths. Yeah. So when they're the same, you always get kind of the maximum reduction. Okay, so once that's the answer for the first part. Then the second part's the hard part. Calculate the charge across this equivalent capacitance. That's the easy part. The hard part's the last part. So once you figured out the equivalent capacitance, here it is. To figure out the charge, so I'll say charge equivalent. That's equal to, well, let's see, capacitance is charge over voltage, so it's capacitance times voltage, and our voltage is 3, right? 3 volts. Yeah, so it's 3 times 8 fifths, 3 coulombs. So the charge is not. What am I doing here? This is volt. Sorry, I got those the other way. Let me make sure they're in the right order here. So when you go back, the capacitance is 8 fifths. 8 fifths farads. The voltage is 3 volts. And the answer is 24 fifths coulombs. Remember, charge is the amount of, basically the number of electrons times the number of charge per electron. So that's the second part. luckily for you, that's as far as you have to remember for the test. But going back, partially is because it takes a lot of time to go the other way. So what you do next is you go back one step. So I'm going to go ahead and draw this in, even though I've got it on a previous page. So here's my battery. Now I've got the three capacitances. I've got equivalent capacitance A, which was, what were the numbers here? 3, 8, and 6. 3, 8. I'll put the units on in a second. 6. Okay. Farads. So those are the three capacitances. So, what we were just showing using the PHET simulation was that the amount of charge that I move through this circuit to these outer plates of this equivalent capacitance are the same as here. So the amount of charge that I have here is going to be the same amount of charge that I have here. That's the outer part, most outer part of this circuit. And because if I have a certain charge on this plate, it has to be matched by the same charge on this plate. And this, I'm taking charge from this plate and moving it to that plate. So we're not really having any electrons flow around in the circuit. All we're having them is flow enough to charge the capacitors, and then we're done. So what we can say is for all three of these, so the charge, let's say the equivalent charge for A is equal to the equivalent charge for B, which is equal to the equivalent charge for C. Those are all the same. And the capacitors are different, so to find the voltage, and I'll do one, you can do the others. So to find the voltage across equivalent capacitor A, it's going to be equal to, again, I always forget which way it goes, so I just have to write it out. Capacitance is charge over voltage, so voltage is charge divided by capacitance. So the charge I get from my previous step here, which is 24 fifths. So I've got 24 fifths. Charge is coulombs divided by the equivalent capacitance, which is 3 farads. And so what will that be? That's the same as 24 fifths times 1/3. So that can be simplified down to 8 fifths. So that's 8 fifths volts. So I want you to go ahead and do the same thing for B. Use 8 farads. 8 farads here. You keep the numerators the same for all of them. So do it with 8 farads, get a number. Do it with 6 farads, get a number. See what it is. So you can see that for equivalent capacitor B, we get 3/5 volts. So all I did was I just took the charge and multiplied by the reciprocal of the capacitance. So I left that step out, first step. So 24 divided by 8 is 3, so you get 3/5 volts. The last one, you got 24 divided by 6, which is 4, so you get 4/5 volts. And notice that the sum of the voltages, 8/5 plus 3/5 plus 4/5 equals 3 volts. Has to work out. Yeah.
So if we were calculating the voltage, doing the same thing in a parallel circuit, would we keep the charge the same and change the...
Well, we'll do that. That's our next step. When we go one more step back, we're going to have 3 sets of parallel capacitors. What happens there is the voltage is the same, but the charge is different. But the sum of the charges always has to be equal to the equivalent charge for all of the parallel capacitors. So instead of, because what we have here is we have one single capacitor, but that's the result of 2 parallel capacitors. So those 2 capacitors they hold this much charge. The sum of the 2. So these 2 will hold, the sum of these 2 that constitute this first equivalent capacitance have to add up to this. These 2 have to add up to this, and these 3 have to add up to that. So let's just do that next. So let's add a page. So now we go back to the original layout. So maybe I'll just steal that instead of having to redo it. So I'm going to take my original circuit here. So what happens at this point is that these voltages that I calculated, so I have this equivalent voltage A, that's equal to 8/5 volts. So I have that voltage across both of the capacitors. Then I have equivalent capacitance B, which is 3/5 volts. And then I have equivalent voltage, well, it's equivalent, but it's also the actual voltage across here. So the voltage across these 3 is going to be 4/5 volts. So the previous step, when I had series capacitors, they all had the same charge. When I go to the next step, these will all have the same voltage. The sum of the charges will be equal to the sum of each one. The sum of this will equal the sum of this will equal the sum of that. So all the charge. Because go back to my original single capacitor, I calculated the amount of charge to be 24/5 coulombs. That's how much goes to here. But if I go back to my original circuit, it really comes here and then it has to split equally. It has to be split between these 2 so that the total at this point is the same as this total here, which is the sum of the 2. So again, I'll do the first one for you guys. So what we're going to say is, we'll say for part A here, which is the first 2 capacitors, same voltage across 1 farad and 2 farad capacitors. So let's write out the equation again. Capacitance is charge over voltage. What we're trying to figure out is the charge. So Q is equal to capacitance times voltage. So here's my voltage, and there are my capacitors. So I'm going to say the charge on, are these all different? No, not quite. But for A, for the 1 farad capacitor, it's going to be equal to the the capacitance, which is 1 farad, times the voltage, which is 8/5 volts. So you get 8/5 coulombs. And the charge on the 2 farad capacitor
is going to be 2 farads times 8/5 volts, which is 16/5 coulombs. And if I add the charge on the 1 farad capacitor plus the charge on the 2 farad capacitor, I'll get 8/5 plus 16/5, which is 24/5 coulombs, which is what I got all the way back here. Okay. So that's, and you should have the same thing happen for B and C. So the only thing that's going to change is you use 3 farads. Well, use this voltage. So it'll be 3/5, and you'll use 3 and 5, and you'll get 2 charges, and if you add them together, you should get 24/5. Not very good 5. I don't want to try that. So it's 24/5. So go ahead and do the next one. And the same thing on the third one. The voltage will be 5/4 volts. You'll have 1/2 farad, 2 farads, and 7/5 farads. You'll have 3 charges. The sum of those 3 charges should equal 24/5 if you did it right. So you should see people with their pencils working on this. Please. Again, I'll give you, people weren't paying attention to me. So the next one, you'll have like 3 farads and 3/5 volts. And you'll have 5 farads and 3/5 volts. That'll give you the 2 charges. This whole idea of taking complex circuits and simplifying them down as much as possible is something that's used a lot in electrical engineering. I was never very good at it when I took the class. It confused me. There's this thing called Thevenin equivalent, which I'm going to look up here in a minute when we finish this. All I remember is I didn't understand it. That's why I was glad I was a mechanical engineer, not a civil engineer. I mean, an electrical engineer.
So there's my answer, which must be right because they added up. So for the part B, charge across the 3 farad capacitor was 9/5. Charge across the 5 farad was 15/5. 9/5 plus 15/5 is 24/5. Then for the 3 other parallel capacitors, capacitance times, they all have the same voltage of 4/5 volts. So here you get 2/5 coulombs, 8/5 coulombs, 14/5 coulombs. You add those together, you get 24/5. And I always do this just because I make mistakes. So if you have it's like an error check on a computer code. If you make a math mistake, you're probably going to find it at that point. So that's it for that. So that's how they work. It's pretty simple math, pretty straightforward. Once you do a couple of them, it's fine. Okay, let me search for this thing that I was telling you about, because it's one of those things I need to go back and remember what this means, because I always bothered. It was one of the I shouldn't say one of the few things, that sounds like I'm bragging, but it was that class was the one that gave me the hardest time. Oh, and I can't even spell it right. Thevenin's theorem. As originally stated in terms of DC resistive circuits only, Thevenin's theory holds that any linear electrical network contains only voltage sources, current sources, and resistance that it consists can be replaced at terminals AB by an equivalent combination of a voltage source in series connection with a resistance, the Thevenin resistance. So what that means, what you have over here is this is a voltage source because you've got the plus minus thing. These arrows, these are voltage sources. And then these are resistances. So you've got 5 resistors. You've got 2 current sources and a voltage source. And what it says is you can simplify that and replace this whole circuit with one voltage source and an equivalent resistance. And if you were to look at the behavior of this circuit at these 2 terminals, so you've got 2 wires, kind of like the wires we brought out of our Arduino. If you looked at the behavior of the voltage associated with this circuit, it would be exactly the same as the voltage associated with this simplified circuit. And it's a lot easier to analyze this simplified circuit than it is to analyze this complex circuit. So that's the whole idea. See, yeah, and it's the same basic idea. It's more difficult to do. And there's probably, let's say, notice this word voltage divider. That was what we were using to, we had the 2 resistors, the fixed resistor and the variable resistor. That's called a voltage divider. So that's what it looks like. So we had our 5 volts in, we had ground. We were measuring the voltage between the 2 resistors. This would have been the variable resistor. This would be the fixed resistor. They're using Z's there not because they're falling asleep, but because Z is, we'll find out later, is a symbol used for what's called impedance. And resistance is part of impedance. What does it say? A simple example of voltage divider is 2 resistors connected in series. Yeah, that's what we did. With the input voltage applied across the resistor pair and the output voltage emerging from the connection between them. Now, what we did was called a resistive divider. And you can see this equation, the ratio of V out over Vn. Vn was 5 volts, V out was what we're measuring. R2 would have been the variable resistance, and R1 would have been the fixed resistance. And that's the equation I think I wrote on the board. But you can also have a configuration where you have a resistor and a capacitor. And what that does is, it's called again, we'll talk about this later, but if you have a capacitor there instead of a resistor, it's called a low-pass filter, which means it passes alternating electrical signals, something that's oscillating. It'll pass low-frequency signals, but it'll attenuate or cut out high-frequency signals. So that's a low-pass filter. You can also, I don't know if they have a high-pass filter or not, but there are filters that are filters, yeah. So it's kind of like well, you don't have that much control anymore because you're listening to it on your phone, but back when you used to have a stereo, you had treble and bass, and you would turn up the bass. What that did was it attenuated the high frequency and accentuated the low frequency, and you heard the bass sound. I guess you see that now, they have different, is this pop sound or is this whatever kinds of different sounds, and what they're doing is they are emphasizing, some of it has to do with just the instruments they're playing, but you can also just take a recording, and by emphasizing different frequencies, you can get a different kind of music sound. Yeah.
So do they use voltage dividers for like a dimmer switch, or even like the plug converter you brought in the other day?
The plug converter, what they do there, that is, so that's interesting. So that's called a transformer, and that's what's hooked up to my computer here, which is warm. So this is a transformer, and what it does is it takes voltage at 120 volts, and it reduces it down to about, 15 volts, something like that. I think So if I put 120 volts into this computer, it would blow up. Okay. So these computers are designed for lower voltages. Once this goes into the computer, there's probably what's called a voltage regulator. So you want this voltage coming out of your transformer to, and also this is an AC signal, so this is varying with time. Computers run off DC signals, which is a constant voltage. The Arduino is a constant voltage. We're dealing with a constant voltage. So besides, this reduces the voltage, and then it goes into the computer, and it regulates the voltage, and it changes it into a constant voltage. Okay. This here is using stuff from chapter 21-ish on the old book. So when we get to that, it's changing the voltage by, it has coils of wire with different number of wraps of coil, and so it changes the voltage that way. Now, the little converter I brought in the other day, it's much lighter. Doesn't have, if it's heavy like this, it's like the interfaces. They have those big, heavy honking things that you have to move around, right? That's the old 20-year-old technology, and those are really heavy. And the heaviness is because there's also iron in there. There's wire wrapped around iron, like an electromagnet kind of thing. These are newer ones, which they figured out how to do it more efficiently. The plug that I brought in actually uses more of DC stuff. So what it does is it's hard to explain, but it does change the voltage. It's changing from line voltage, which in Europe is 240 volts, down to whatever the voltage is on your USB, which is, I think, 1.5 volts maybe. But if you had to have an old school transformer with your phone, you'd have a transformer this big and your phone that big. So they've come up with other ways of changing the voltage that are more efficient and in terms of weight and size. But I'll wait to discuss that. It's to do with turning something on and off at a high frequency, and it allows you to get much more efficient change in voltage than using iron cores wrapped with copper wires. Okay, somebody asked me about a test, physics. So since we have a calculus test on Tuesday, I'm going to wait till the following week to do the physics test. I know it's delayed, and I apologize for that, but I don't think you want to take it next Wednesday. So this material we just covered, plus just calculating voltages due to point charges, which we did in class, calculating forces on charges, which we did in class. So we're going to have a test on the material associated with chapters 15 and 16 homework. And so there'll be a review. I'll put up a review sometime next week that you can watch. We're going to move on to the next chapter, which is chapter 17 material. We're finished. We'll just start on that today. So whether it'll be Monday or Wednesday, probably Monday, just because I don't want to, I know you guys don't like having that big a gap between the time we finish the material. So as far as chapter 16 homework, that should be done by next, I was going to say Friday, but if we have the test Monday, so would you rather me? But then Wednesday is the day after the calculus test, so I'm going to say Friday. Okay, so you may have already done it, but just if you haven't done it already, make sure you have it done by next Friday. I might just grade it in class and hand it back to you if you need it to study by. That's the only reason I'm concerned about that. Okay. So we'll tell you more about, but you can put that, we'll say it's going to be Monday, not next Monday, but the following Monday. Just means you don't have as much, you've got an hour and 15 minutes or an hour and a half. Okay, so this is an introduction to the material in chapter 17. So what we've dealt with so far is we've dealt with voltage is electric potential. It's basically pushing the electrons, it's creating an electric field in a conductor and is pushing the electrons one direction, and so you end up with part of the circuit that has an excess of electrons and another part of the circuit that has a deficit of electrons. The device or the circuit element that uses that the most is the capacitor. And that's what this is, just to remind you. We just talked about it, so you don't need to write all that stuff down. Okay. So now what we're going to talk about is current. We've talked about current to some extent already because I've said make sure you put a resistor in with the LED. Because if you don't put a resistor and you just run the LED, the current is going to be too high, and that may fry the Arduino. Okay, so we've dealt with the concept of current. Current is equal to the amount of charge that flows through a cross-section of your wire per unit time. So it's kind of like flow rate, but it's flow of charges. And what's causing this flow of charges is an electric field that's been applied to the ends of the wire. So because charge is coulombs, and the time is seconds in our unit system, the units for current are coulombs per second. But again, we define this new quantity called an ampere or an amp, and we use the symbol capital A. So if you see A as units, it's amperes. It's basically coulombs per second. And what this is showing is that, just showing the electrons moving, I think. So the interesting thing, okay, this is a history thing. When we talk about current, it was developed, the whole idea of current was developed before we knew about electrons. We just knew something was happening. Ben Franklin, flying the kite, got electricity to move through this wire to to the jar. And what he thought was there were positive charges and negative charges, but he didn't know why they were there. And so by default, they defined the movement of positive charges as the direction of the current. But the reality is the positive charges don't move, the negative charges move. So it's a little, so when we talk about current, we say there's current flowing in a wire. It's kind of like convention and actuality. So from a convention standpoint, we've got a wire, and if we have current flowing in this direction, so there's the current, and it's moving from left to right, what's happening is we're saying that the positive particles are moving from left to right. Okay, so these are all going this way. But the reality is, but we spend so much time developing stuff that they decide to stick with the reality. If the current is going this way, what's really happening is that the electrons are going the other way, because those are the things that can move. The net effect is the same. I'm moving positive charge this way, so negative charge has to move that way. So here, negative charge is moving that way, so positive charge has to move the opposite way. So you kind of have to blank out the reality and just think about it as positive charge and moving in the direction of positive current. Not worry about where the electron is going. Okay. And if I went to what this is kind of a average of a whole bunch of electrons, and it's if I'm talking about constant current, everything's happening fixed, kind of like in the Arduino, we're applying a constant voltage, so we also get a constant current. But you can also have the current varying with time, and that's what is happening here to the wall. The current is not constant. The current is actually going this way and then that way and this way and that way and that way, so just going back and forth like that, instead of going one direction. It's actually oscillating back and forth. And as a consequence, if we have a current that's changing with time, we use a small case I. And that's because the amount of current that's passing is changing is a function of time. It's not constant. And it can be positive or negative. If the positive particles are going this way, then it's a positive current. If the positive particles are going this way, the other way, it's negative current. Likewise, in this situation, if you had a time-varying current, you'd also have a time-varying voltage. So anytime you have time-varying some quantity, now the resistance would not be time-varying, the capacitance would not be time-varying, but the voltage and current would be time-varying. So this is for varying current and voltage. If we were dealing with constant voltage, and this is constant, we use capital letters. So I don't put of t because it's not a function of t, it's just constant. Now, we've used resistors a lot, and we've used them with constant voltage, hence constant current. And it turns out that resistors have a linear proportional relationship between those two properties. The voltage, which is the electrical potential, and the current, which is the flow of electrons. So when we're running our little voltage divider, what's happening is we're pushing current through both resistors. And the amount of voltage across each resistors depend upon the resistance. So the higher the resistance, it turns out, for a given voltage, the higher the resistance, the lower the current. That's why we put the resistor into the other part of the circuit, the LED part of the circuit. We just draw
draw a picture. So here, if we have our voltage, and then we have our LED. I don't know how to, I guess it looks something like, maybe like that. This is our LED. There's the resistance to current in an LED is pretty small. So if you just put your LED in here with 5 volts, the current's going to be really high. It's going to overheat the LED. So what we do is we put in our 220 ohm resistor, and most of what this is doing is limiting the amount of current, and the amount of current is going to be equal. If I solve this relationship between resistance, voltage, and current, the current is going to be the voltage divided by the resistance. So in our case, we have 5 volts applied to the Arduino, and we have 220 ohms, and so the amount of current that's flowing through that circuit, assuming that the voltage drop across the LED is small, it's going to be 5 divided by 220, which is equal to 0.0227 amps, or 22.7 milliamps. So when you guys stuck in the wrong resistor, you put in a higher resistor, you limited the current to even less, and then it didn't, then it was dull. Okay, so that's it for right now. So chapter 16 homework. If you haven't already started working on it, it's time to start working on it. Get it done by next Friday because you're going to have a test the following Monday.